Alright, welcome to section 4.4, and we will talk about concavity and curve sketching. Now, what is concavity? Observe the graph of y is equal to x cubed. This is our graph, y is equal to x cubed. The lines tangent to the curve are above the curve when we're looking at the interval from minus infinity to 0. You see all these lines tangent to the curve and they are above y equal to x cubed. Now, look at the lines tangent to the curve from 0 to infinity. They are all below the or under the curve of y is equal to x cubed. Now, this kind of behavior is what we call concavity. And in particular, if the derivative, right, see how the steepness changes? So it's steeper here and then it's not as steep going to 0. So that means your f prime is decreasing. Now, in the other side of 0, to the right of 0, you start with a smaller slope, and then the slope increases. You see this, the lines tangent to the curve are getting steeper, so the derivative there is increasing. So the graph is concave down if f prime is decreasing on that interval, and then it's concave up if f prime is increasing, or f double prime, if you think about it, f double prime would then be positive. So here f double prime would be negative when it's concave down. So f double prime is positive when it's concave up. Okay, let's define it. The graph of a differentiable function y equal to f of x is concave up. It's referred to be concave up on an interval I, as in the case in the previous slide. It was from minus infinity to, or rather from 0 to infinity, and the other one is from minus infinity to 0. So it's concave up if f prime is increasing on that interval, and it's concave down if f prime is decreasing. So when you have f prime increasing, think about it, that means its second derivative would be positive. If f prime is decreasing, that means its second derivative is negative. The second derivative test for concavity. Let y be y equal to f of x be twice differentiable. It has to be twice differentiable. We have to take the second derivative of the function. If f prime is positive on that interval, the curve of that function over that interval is concave up, meaning it holds water. So you have something that holds water either this way or, okay. Now, f double prime, if it's negative on the interval, then the graph is considered concave down. So it holds it spills water. So it could look like this, or something like this, or like that, right? So whenever you have a change of concavity, so a point where the graph of a function has a tangent line and where the concavity changes, it is called a point of inflection. Here are just a few of what may look like. You have a line tangent to the curve that way, and you see that it's concave up here on this side and concave down on the other side. Here you have a concave down, and then on the other side of the point it's concave up. Another possibility would be concave down this way and concave up that way. So all of these are examples of a point of inflection. So whenever the derivative, the sign of the second derivative, changes from positive to negative, negative to positive, either way, these are called points of inflection. Okay. So let's see whether 0, 0 of the graph of the function y is equal to x cubed is a point of inflection. Let's take the second derivative of the function f of x equal to x cubed. Y prime is, okay, what is y prime? It's 3x squared, and then the second derivative would just be 6x. How do we get the point of inflection? Well, just like your first derivative, to getting the local max or min, we set it equal to 0. This time we take the second derivative and set it equal to 0. And this is just saying that, well, x equal to 0 is a possible point of inflection. It's a critical number, and we just have to test to the right of 0 and to the left of 0, test -1 and test 1. I always encircle my test points, that way you can distinguish that, and this is where our interval is divided, or our number line is divided. Okay, so what is y double prime of -1? Well, that's just 6 times -1, that's negative. Notice that we are only concerned about the sign. We don't have to know the value. All we need to know is the sign of the second derivative. Now what about, so it's negative there. What about y double prime of 1? That's 6 times 1, so it's positive. So 6 times 1, that's positive. So you have a situation where it's concave down and concave up. So we can conclude, therefore, that at x equal to 0, we have a point of inflection. So this is a point of inflection at 0, 0. Now let's see, does the graph of y is equal to x squared have a point of inflection? So let's take the first and the second derivative. First derivative is 2x, second derivative is 2. Well, it's constant, which means if it's constant, it stays in one sign. In this case, it stays positive. That's why if you look at the graph, all the lines tangent to curve are always below the curve. So we have a concave up, or another way of looking at it is that the derivative, the second derivative, is always positive. So this function is concave up all throughout its domain. So because there's no change in concavity, it's always concave up, then we say that f of x equal to x squared, this has no point of inflection, because there was no change of concavity. Now, we know from our critical point in finding the local max or min, either the derivative is 0 there, or the derivative fails to exist, like it's undefined, if the line tangent to the curve is vertical. Now the same thing with a point of inflection. At a point of inflection, it's either the second derivative is 0 or the derivative fails to exist. So let's see, let's find the points of inflection for this function. And it's the blue curve. It's just the sine function that's translated vertically by 3 units. And what we do is we take the first derivative. Y prime is 0 for the derivative of 3 plus cosine of x. Take the second derivative. Second derivative is negative sine of x. Now we are looking at the interval from 0 to pi. So we set that equal to 0. What is the angle from 0 to 2 pi rather? From 0 to 2 pi in the interior, which makes the sine of that angle equal to 0. Because if you multiply both sides, really we're looking at sine of x equal to 0. We multiply both sides by negative. Therefore, x is, what is the angle between 0 and 2 pi exclusive? And that would be pi. But in general, if you're looking at the whole domain, all multiples of pi would make the sine of x equal to 0. So let's see whether this is a point of inflection. Right now, it is a critical point or a critical number for the point of inflection. So to test whether pi is a point of inflection, we take 2 x's to the left and to the right of pi, and so I'll take, say, pi over 2. It has to be contained in this interval. We can't go too far to the left. And then 3 pi over 2. So these are our test points. And let's look at the sign of y double prime. So y double prime means that we plug in pi over 2 into negative sine of x. So what is the negative of sine of pi over 2? That's just the sine of pi over 2 is 1. So negative 1 would be the value, which means the slope is, or rather the second derivative is negative. Okay, so what do we say? That means it's concave down. Now what about at y double prime of 3 pi over 2? So we take the sine of 3 pi over 2 is negative 1, then take its negative again, so we get positive. So y double prime is positive on the interval from pi to 2 pi. So we have that it's concave up. And so we conclude therefore that our point pi 3, because we plug in pi into the original function, and we get that y is equal to 3 plus 0, which is equal to 3. So we conclude that pi 3, the point pi 3, is a point of inflection because of this change of the sign of the second derivative from negative to positive. See, this is the graph of the second derivative. So, which is consistent. If the second derivative is negative, that means you have the graph, the original graph, being concave down. If the sign of the second derivative, sign meaning SIN, I'm sorry, SIGN, the sign SIGN of the sine function of the negative sine of x is positive from pi to 2 pi. That's why it's concave up. So we say that pi 3 is a point of inflection. Okay, find the points of inflection of the graph of the function y is equal to x to the 5/3. And here is the graph, and we see from this that 0, 0 is a point of inflection. This is an example in your book. It's example 3. But let's verify. So we'll take first derivative. Y prime is 5/3. X to the 5/3 minus 1 would be x to the 2/3. Now you take the second derivative. So you multiply 5/3 times 2/3, you get 10 over 9. X to the, 2/3 minus 1 would be negative 1/3. And if you observe here, if we put this at the bottom, because if it has negative exponent, we're going to get 10 over 9 cube root of x, because x to the 1/3 is the same as cube root. And when you set that equal to 0, it will not be equal to 0 in the sense that the numerator will never be 0, but, okay, y double prime is undefined when x is equal to 0, because that will make the denominator equal to 0, and that means it's a candidate for a point of inflection. So let's go ahead and test the sign of the second derivative. So this is our critical number for point of inflection, so 0. Okay, so now we take a number to the left of 0. Negative 1 is our test point. 1 to the right is our test point. So what is y double prime? Well, look, we'll plug in negative 1 in here. And so what is the sign of the whole fraction? It'll be negative. So y double prime is negative. And then to the right of 0, we plug in 1 into x, and the cube root of 1 is just 1, so the whole thing would be positive. So we have a concave down and a concave up, so that means at x equal to 0, we have a point of inflection. So that verifies that indeed at the origin, because we plug in 0 in here, even though the second derivative fails to exist, but it is a point of inflection because of the change of sign of the second derivative from negative to positive, or concave down to concave up. Then we have a point of inflection at x equal at the point 0, 0, or at the origin when x is equal to 0. find the points of inflection of the graph of the function y is equal to x to the fourth. Let's see, do we have a point of inflection for this fourth power of x? So let's take the first derivative. Y prime is 4x cubed. All right, y double prime is 12x squared. Now we set that equal to 0 and we observe that x equal to 0 is a critical number. The question is it a point of inflection? So we have to test the sign of y double prime to the left of 0 and to the right of 0. But it's very clear here that if we test -1 and 1, what is the sign of y double prime? But since the second derivative is always x squared, that means it's positive here and positive on this side. When there is no change of sign to the left or right of a critical number, then that means x equal to 0 is not a point of inflection. And as you can see from the graph, it's concave up to the left of 0. It's still concave up to the right of 0. And so an x to the fourth is very similar to the quadratic function. It's just flatter near 0. Okay, so this, just because you set the derivative second derivative equal to 0 and you get a critical number, that does not automatically give you a point of inflection. It's just so happened that the second derivative there is 0. Find the points of inflection of the cube root of x, because x to the 1/3 is the same as the cube root of x. So let's take y prime. So it's 1/3 x to the -2/3. Then take the second derivative. Y double prime would be what? That gives us 1/3 times -2/3 would give us -2/9. And then you have x to the -2/3 minus 1 would mean that x to the -5/3. Then you rewrite this as the negative of 2/9 x to the 5/3, which again will mean that y double prime is undefined when? Okay, when x is equal to 0, because the denominator will make it 0. So what do? We'll find out whether this critical number is a point of inflection. So you take 0, again you test it to the left and right of 0 and find out. So -1 is our test point and 1 is our test point as well. So just plug in -1 into y double prime. So look at this. You have the cube root of -1 because that refers to the denominator. So it's the cube root of -1, which is -1. Raise it to the 5th power, you still have negative. So negative over a negative means that its y double prime is positive. Okay, now what about to the right of 0? We test 1, and this will just be positive, and the whole ratio would then be negative. So we see here that there is a change of concavity from concave up to concave down. So it's concave up to concave down. That concludes that x equal to 0 is a point of inflection. So indeed, you have a point of inflection at x equal to 0, where in this case, y double prime is undefined there. But as long as we can plug in the value of x into the original function and there's a change of sign of the second derivative to the left of 0 and to the right of 0, from positive being concave up to negative being concave down, therefore x equal to 0 is a point of inflection.